Okay, the third and final thing we're going to review for flownets is how to deal with anisotropic soils with the Laplace equation, kx is equal to ky, and what happens if kx is not equal to ky? Can you draw a flownet? And the answer is yes, you can. So here's the governing equation that we used for the flownets that we've dealt with thus far. Notice there's no k, kx equal to ky, so they both become k, and you divide by k and they're gone. But for anisotropic soils, we have a kx and a ky, and the impact of this is for a proper solution to this equation, the equipotential lines and the flow lines no longer intersect at right angles. Well, wait a minute, doesn't groundwater always flow in the direction of maximum head drop? Not necessarily. If the hydraulic conductivity in each direction is different, then it might be skewed. So the way we deal with this, there's a little trick we do. We perform a coordinate transformation. And so we basically do a coordinate transformation for the x coordinate only. We leave y the same, but we're basically going to scale x as follows. So we're going to come up with this new x coordinate called x bar that's equal to x times the square root of ky over kx. Why the square root of ky over kx? Because it turns out that if you use that coordinate transformation and you go through this full derivation, and now this derivation is a little bit long. I'm not going to go through the whole thing. You can pause the video and stare at this if you like. We take the derivative of this transformed x, and we end up with the second derivative, and we come up with this term del h squared del x squared is equal to, of the original x, is equal to the second derivative of h with respect to the transformed x multiplied by ky over kx, this ratio. And if you plug that back into the Laplace equation, then these kx terms cancel, and you're left with ky and ky, and since those are equal, you can divide by ky, and you end up with this form of the Laplace equation, which is exactly the same as we had before, except now we have the transformed x plus the original y. In other words, if you use this coordinate transformation on the right, you end up with a Laplace equation using that transformed x and y. In other words, if you transform your drawing, you can draw a normal flownet, as long as you do that transformation. So what does that look like? So this is a problem. In this case, we have a sheet pile, and it has a clay blanket, and there's water up here. This zone down here, it's shown in white, but this is all saturated soil. So the water is going to come down here and go under this blanket, down under this sheet pile, and up to the other side. And in this case, kx is equal to 4 times ky. So this is the true scale. But in order to draw a flownet, we are going to perform our coordinate transformation. And using the equation that we derived, we say, let's go back to the equation. You take the square root of ky over kx. So in this case, the transformed x is equal to the original x times the square root of 1 over 4, which is equal to x over 2. So what happens is you basically shrink everything in the x direction by a factor of 2. Now, I've drawn a lot of flownets this way, and what I do is I create my original drawing in a drawing program, and then I just group everything, and then I resize it you right-click and change the size, and in this case I would just make the width 1/2 of what the width was before. And you end up with this version, which in this case has been shrunk by a factor of 2 in the x direction. Then you draw a flownet solution using that compressed scale, the transformed x. You'll notice that we have, I'm pretty proud of this, I drew this one myself. We have these nice well-formed cells, and that looks like a pretty decent solution to the flownet. Then you take this solution, and if you're in a drawing program, you just group everything again, and then you stretch it back out to the original scale. And now we have a solution for that anisotropic case. And we can do the same thing we did before. We can look at different points in here, scale the head value, calculate pore pressures, and we can even calculate the total flow rate through this solution. But we have to do that a little bit differently as well. To get the flow rate, this is our original scale. For a cell, we have QX and QY. And in this case, QX is different than QY since we have anisotropic soil. QX is equal to KX times the hydraulic gradient and X times dy. Dy is the width in the y direction. And QY is equal to KY times the hydraulic gradient in y times the width, which is dx. And again, if we go back to our transformed scale, we have a QX, the total, now we have a dx transformed and a QX transformed. And remember, dx is equal to the original x times the square root of ky over kx. And so we have to change how we calculate the hydraulic gradient in the x direction. It's equal to I times the square root of kx over ky. And with that, we can plug that into our delta Q transformed. And the Q at the natural scale is equal to the delta Q transformed if kx equals the square root of kx over ky, and ky is equal to, the sum transformed k times ky over kx. And therefore, if you declare a new transformed k as a square root of ky over kx, you can use our original q term, k nf over ne times h, as long as you use this k. So the bottom line is you count the number of flow channels, you count the number of equipotential lines and the total head loss like we did before, and then you combine kx and ky into this single k bar, k transform term, and you have the correct flow rate through your flownet solution to anisotropic soils.